Okay, yeah, so let's get into it. So when we brought this up during the organization, some people said, oh no, talking about systematics, I'd rather not, because I only do if I have to. Right, you remember, Gordon? And it's a topic that can be really cumbersome in your analysis, because you have your nominalist selection, which you devised within 3 months, and then it takes half a year to evaluate all the systematics. So it's really hard on the people who are doing analysis, and you have the prescriptions by experiments saying like, okay, you have to evaluate this and this and this and this, and everybody has to reproduce this in their analysis. So it's a lot of work which we're repeating over and over. And then the next thing is, can we compute this efficiently? And you will see that sometimes we cannot, and it requires a lot of effort to actually do this well, right? So you have seen similar depiction of how the analysis pipeline works today already. And we're somewhere here at the last steps where we are having our data reconstructed, and then we have to skim this and create some kind of analysis format. And here is already important how we do the analysis format in how we later can compute the systematic uncertainties. Or maybe we try to push this upstream and have some uncertainties run centrally, and then only the end results are in the final n tuples. So we're somewhere here in this part. And when you talk systematics, I would personally say there's kind of 3 types of systematics you can have. There's first of all the weight systematics. So this is a place where there's just the likelihood of observing an event that's changing. So you apply a different weight, but everything else in the event is the same. So they are relatively cheap to compute. And this is biased from my experience in Higgs2BB and Atlas. I don't know if I can move this. Yeah, not really. So in our analysis, we had about 150 of those weight systematics. And then you have the more ugly ones, the object systematics. So here it's really the PT of a jet changing or something. And that affects the entire selection that you have to do in your event. Events might be showing up suddenly in your histograms, or they might be killed. And this requires some more computation. So you have to rerun more stuff. And then there's this ugly rest. So those are systematic uncertainties, which are very specific to analysis. And you might have to use very strange techniques to estimate them, and probably it's not on a sound statistical ground, and I cannot talk about those because they're different everywhere. No, the slides are not advancing. Okay, and you have seen this before, right? We have our CPU and disk models, and we're afraid that we're not going to reach this 20% budget increase, so probably we're further down. And then depending on how you aggressively R&D or not, we might manage to get it done or not, right? So where are the systematics in this picture? I would argue they're actually quite important, because we have seen this morning the 4% analysis computing in CMS, and we got the admission is a made-up number. And I'm sure here also in Atlas, it's also a made-up number, and this is the aggressive R&D part. So they are projecting 7% CPU usage for analysis. But I would argue that is only analysis. There's also Monte Carlo derivation, so the process of making the final analysis formats, and the systematics, they are somewhere here in between. And if you compute them inefficiently, those 7% might be actually bigger. And the same for the disks. So you have the other, which I assume is analysis n tuples. And then you have also the DAOD Monte Carlo production. It's a bit Atlas biased because it used to be in Atlas. But in CMS or in other experiments, it's going to be the same. So we're somewhere here in this business. And if we do this wrongly, we're actually wasting a lot of resources. And then also, I'm glad the question came this morning. There's the kind of secret computing, the shadow computing. I don't know if you have ever logged into LX Plus and the machine was slow. And then you type top, and then you see 8 instances of CMS SW running. Right? They're not showing up in this plot here. And nevertheless, they're evaluating systematics, right? So, and then you have the university cluster that nobody knows about, only the people at the university, and they're running entire nights on this cluster evaluating systematic uncertainties, okay? So it's something we have to take care of, and we have to do this correctly. And the classic way of how you would evaluate systematic uncertainties is you have some event, you run some calibration steps, some selection, then you make plots or you make n tuples. And then your professor comes and says, good, and now we need the systematic uncertainty. And what does a PhD student do? Well, of course, they just say, okay, let's just switch the muon calibration to some systematic uncertainty and resubmit the job. Because this is the easiest thing you can do. You change 1 line, 2 lines of code, and then you submit a new job. You have a new n tuple, and those are the varied quantities. And I've seen this in real life. I've done it in my first weeks as a master student, then I very, very quickly learned that this is a stupid way to do this, but it's happening, right? So the question is now, is this better? So you say, like, okay, I will do one job and then I will just rerun all my events and then make this loop over the systematic uncertainties and have those tools. You know, in Atlas, it pretty much looks like this. I took the inspiration from a talk that Niels gave in the analysis working group. So now it's better because you're only running one job. However, if you don't watch out, you're running this systematics group also for your weight systematics, and you're rerunning the selection. You don't have to, right? And then you're running this 150 times and wasting a lot of resources again. And it's also not a very smart way to do this. And maybe you're saving one n tuple for each run. And then you have wasted 200 times the storage space. So the better, of course, then is, okay, let's only do this for the object systematics. So maybe it's like 13. And then find a way of how to transfer the weights from the calibration step to the plotting step, because then we're only replicating the plots and we're filling with one quantity, we're filling 150 plots and they all have different weights, or you have a multidimensional histogram. And I think this is where most analysis groups are today. The experiments, they kind of leave them alone and give them the systematic tool. And then they say, oh, now you figure out how you do this efficiently. I mean, we see that this is changing. I mean, we had a talk also in the analysis working group where CMS was telling us that they're trying to do this a lot better. But it's really on the shoulders of the different framework authors to make this run efficiently. And the question is whether we shouldn't do this a bit better and more upstream and take the work from them. So the best these days might be the columnar approach, where you have your weights magically going to the plotting stage, right? You tell your data frame thing, those are my weights, and I want to replicate this histogram. And then also you run all the object variations, and then your thing will understand how to run this calibration and selection multiple times, also kick out the ones that don't survive the selection, don't fill. And the user kind of says what, and then the frameworks, they know how. Okay. And the question is, can you do this today? And the answer is yes, you can. So right now in a data frame, you could run something like this. You get your calibration tool from the experiment and conveniently left out all the configuration. So the metadata stuff to set up the thing that is doing the correct calibration, just left it out, but it's something that the analyzers have to do. And then you say, okay, I want to run this calibration. You have to write a bit of code. Okay, fine, that's what we can do. And now the future is going to be that you have also this vary functionality where you say, and I want also for this mu and pt apply the following variations, and then the data frame thing figures out automatically how to rerun all the analysis steps that have to be rerun, and then to replicate the histograms or make more n tuples and do everything for you. I know that the coffee people are doing the same, so I think this is a very good development. But the vision, of course, should be that you say, okay, my experiment applies standard calibration and systematics, right? You give them a package, and this package will do the right thing also at the right time. So when the calibration constants change, you rerun and you get a new thing, right? Of course, you will have to do some configuration. You will have to select what you want, and it's probably stupid to rerun your job and suddenly everything changes because overnight they have new constants. It should be a conscious choice probably, but it should be something that we do in a more centralized manner. So it's not on the shoulder of all the people. And then the question is, how does this tie into the new analysis formats? So if you do this columnar thinking that the data frames are doing, you have some columns, the varied data as they come from disk, and then you're varying the columns, hopefully on the fly. And then you say to your data frame, hey, the PX, I also want to vary down and I want to vary up, and please rerun everything that depends on it. So it's something which you do for object systematics, and for weights, it's pretty easy. You just create columns for each weight and you say, look, can you please replicate this histogram 27 times and then fill it with those 27 weights? So will reduced analysis formats help us with this? I personally think they do. I wanted to leave the question just here, but then Nick this morning also answered it. So if you have a very slim format, which you can read from disk very fast, and we know that often our analysis jobs, when they run the nominal processing, they are often limited by how fast you can get the data to the CPU, right? You're loading the data, then you decompress it, and then the other analysis steps that you do on top, they're relatively lightweight. So if I can do 27 variations at the same time, then I'm going to put my CPU to good use. And there might be some systematics where we cannot do this, where we need so much information that our super lightweight data format will not support them. And the question we should answer, I mean, it's a thing for the experiments, but we should think about it. Can we maybe recompute some of the systematics with a bit lower precision, and then we just leave out some columns of those data formats, which, you know, in the, well, if you want the true thing, you would take those columns in and do the real computation. But if you say like, okay, but I can get to 90% of the same accuracy if I just compute this with PT and eta of the muon, maybe it's good enough. So it's something that we should discuss. And I think we should strive for systematics which we can compute on very lightweight data formats on the fly. You know, you just have you get the data, the nominal data from disk, and then you can generate the 27 systematics just like this on the CPU. We would save a lot of disk space, and if you're on a slow, if you have to live with slow I/O, you can nevertheless do a lot of work with the few data that are coming because you're reading them only once, right? You don't have to read them every time you want to compute a new systematic. So what is the current status? In our analysis working group meeting, we only had Atlas and CMS, but I tried to ask around a bit. And also, if you look at the root workshop, wait, is it here? I have a link to the root workshop part, but maybe not on this slide. Then you see that what we already have is a unified interface in most of the experiments for the systematics tools. So you don't have to go to every, in Atlas they're called combined performance groups, and then you have to do your own recipe. This is how we did it in run one. You just write a wiki, and then they tell you how to apply all the uncertainties. Now it's all common tools. But those common tools, they're not necessarily supporting this very efficient processing, like getting the weights to the right place and rerunning only the steps that you have to rerun. This is often on the shoulders of the analysis people. But now we're at the point where it's starting to change. So we have the frameworks like our DataFrame and Coffee who are supporting the more efficient processing. And while we're doing the reduced formats, we should also be thinking about how we can do the systematics more efficiently. And also in CMS, I know they are talking already about the all-in-one go systematic from the nano. It's unclear whether they can do it, but at least it's nice to think about it. And then I asked a bit more, LHCb friends, how do you deal with common systematics? And the answer was, what do you mean with common systematics? Everybody's on their own, because this is this thinking of, yeah, we have like this prescription of those following uncertainties which have to be applied. This is a very Atlas and CMS thinking. In LHCb, I was told at least, the analysis, they have so different problems, they're looking at so different things that there's not this notion of, well, 90% of the systematics are the same and only 10% are different. For particle ID, I know it's quite standardized. They even have a paper on it. But, well, it's a discussion which I think should not only be in Atlas and in CMS. I also tried to get the price from the neutrinos, but they're still they have still other things they have to take care of, because sometimes they're not even running. So if you know more in this respect, especially not only in the Atlas and CMS hemisphere, please show up in the discussion because we need you. And now I want to finish with some points we have to consider. So first of all, systematics, they are replication of work. It's work that people have to redo again and again. This is inefficient. And if you have a central tool for everything, it's a black box. And the only downside I can see is that people maybe wouldn't know how a certain systematic is computed. So if I ask somebody who applied this black box, please calibrate everything and give systematics, and ask them, how do you do muon momentum scale variations? They might not know. But the question is if that's a bad thing. How much CPU in this space can we save? Well, it depends how we do it, right? So if we're highly optimized already now in an analysis group, we don't save much. If it's an analysis group which has a pretty young framework, pretty simple one, we have seen orders of magnitude savings by computing the systematics more efficiently. And then there's the point which nobody talks about. If you do a central maintenance of these things, if you have some volunteers who say like, okay, I will write you a systematics package, they don't get recognition for this. If you tell your professor, okay, I have to evaluate the following systematics to get the correct result, the professor will say it's okay, because that's what you need for the result. If you say, I want to contribute to the central maintenance, then he's going to ask, do you have the time for that? Do you get a paper with that? How are you going to apply for your next job? So nobody will give you anything for that. And nevertheless, it's work that should be done, right? So question now is everybody on their own? I think I suggested that they're not. And we should think about how we can help and unify and maybe also disseminate knowledge about how you can efficiently deal with systematics uncertainties. So now I hope I didn't use more of my time. Good.
Okay, it's Columnar, Iowa State University. Maybe, I'm sure we have a long discussion this afternoon, so maybe just if you go back to slide 9, 10, where you say what the workflow is. One of the big things which we did, we are rolling out the new systematics handling in Atlas, is that we actually swap the loop over the tools and the loop over the systematics, so that for every tool we just run the systematics that we need for that tool, or if you were to put that into a notebook kind of approach, it would be like for every line in the notebook, you evaluate just what are the systematics that you need for this particular line, so that you get all the systematics that would change for that line. And then there's a tracking for all the objects or all the columns to know which systematics go where.
I think that's a great development, yes.
Yeah, but there's also, it's very hard to actually get these things rolled out because many people never hear about them, just assume they're on their own. And maybe the other thing with the reduced data formats, maybe the question is the opposite way. Can we get the reduced data format smaller if we simplify the systematics? Because in the end, you won't have a reduced data format if you can't run the systematics that people need on there. If you need the systematics and you can't do it on a data format, you won't use that data format. So
yeah, I totally agree. I mean, it would be a disaster if you have to create 10 times the data format just to run your 10 different systematics, right? So that's pointless.
Yeah, but it's the opposite way. Data format can get smaller if we get the systematic better. Right now it has everything what it needs for the systematics, but it's at least in Atlas, but it's a lot larger than what CMS has, in part due to all the stuff we need for the systematics.
Mm-hmm.
Yes, to Nick Smith, Fermilab. I guess to follow that up, one thing I want to clarify is, yes, you can run all the CMS systematics from NanoAD, and I do, and plenty of people do. And that's in large part due to the fact that they've been developed not with this, encompassing framework CP tools, right? And I'm sure we'll have long discussions about whether or not that, clearly you want to meet in the middle, right? CP tools lives in this, EDM model where you really have to do a lot of expensive work to, calculate these things. And it's not easy to do that in these new frameworks, right? That's what I understand from and from CMS, we started from like very ad hoc things at the end. So it's very easy to do them at the last stage. And, hopefully we come to the middle somehow and we find something that is a flexible tool, but does not require multiple format or multiple outputs or multiple EDM formats. I don't know. Do you think you will be coming down from CP tools, making it more end stage?
It's not me because I'm not in Atlas anymore, so I don't have a say.
Will someone be killing CP tools?
I think the question is not quite framed right though, because the EDM is not really a burden. The EDM can be made as small as it needs to be. And I think the interesting question, because you raised, turning your, you raised having to turn your SOA into an AOS interface, and the EDM already does that. It can be made as small as it needs. What's troubling is the amount of dependencies upstream.
I'm actually happy that there's some dissent here, because I was hoping, that we have something to discuss about.
Yeah, I think let's take one last question from Miguel, and then we can follow up.
Yes, hi, Michel Villanueva from the scene. There are a lot of very interesting ideas on these slides, are quite cool, but I have in mind the kind of systematics that are quite painful and common, like for example, the misalignment that requires to pass again through the reconstruction process with parameters of misalignment, that I wonder if this can be somehow implemented in this idea of including the weights on, I mean, I don't expect to get an answer now, but at least if someone has a good idea of how to do this, because basically all the objects that come out of the reconstruction depend on the alignment configuration. and make these misalignment studies are always painful.
Yeah, this is the stuff that I would put in the red box, right? But yes, if there's somebody who has a good idea, amazing, because we can save a lot of computing time, maybe. Huh? Yeah. Not working.
Thanks. Just wanted to make a comment for LGB, since you made a kind of generalist statement on everybody is on their own. It is in a way, but it's taken out of context. It is true that there's a lot of flexibility, and some analyses are totally different, and so different that you can't really standardize as you had with your kind of idealized few lines of code, right? Which would be the ideal. But we do have a bunch of packages for PID tracking and the trigger calibrations as well. Some of them are even now for run 3 pip installable to make them as easy as possible with the dedicated environments. So it's actually really easy to exploit. So it's not that everybody is really just on their own, but yeah, we're going more and more towards some common things. But in the end, of course, depending on your analysis, you might actually use that or have to go and even fine tune some of those common tools, because then it's not precise for your billion events in charm physics, for example.
Yeah, it's great that you said this, because I got this comment only from one person at SCB, so it's a very biased sample, of course, right? I asked one person, I got one answer.
Yeah.
But this is the thing that we should discuss on the workshop, and it was actually hard to get this information from LSCB. So there needs to be more discussion, and I'm super happy that you now spoke up, and you should come to our session.
I put a couple of comments already in the Google Doc, but okay, fine.
Very good. Okay, cool.